All right, so go Bears. So well, after last weekend, it better be go Bears, right? Anyway, so I had some other jokes, but I'll tell them next week. So homework is due. Anyway, stars. I introduced stars, and let me just make sure I've got all my stuff here. Yeah. And I want to discuss today the light that those stars emit, both the continuous light and also the absorption lines that are produced in the continuous light. And it's those absorption lines that allow us to tell what stars are made of. Okay? So you've got this hot central region, and it emits a continuum. And then, as we will discuss later today, the cooler outer parts produce absorption lines. And it is from those absorption lines that you can tell what stars are made of. And they're mostly not berkelium or berkelium. They're mostly hydrogen and helium, but I have this T-shirt, which I'll show later on. Anyway, stars differ from basketballs and other things in that you see yourselves or basketballs as a result of sunlight or light from all these light bulbs reflecting off of the basketball or your T-shirt or whatever. That's reflected light. That's not light that's generated by the body itself. However, the basketball does have a certain temperature, and it's got jiggling motions going on inside, and those jiggling motions do produce light. It's just infrared light, and you can't see it. Okay, but snakes have infrared detectors that can detect warmth or infrared light, and the military uses infrared detectors that can detect tanks during the day or night, doesn't matter. Anyway, stars also emit radiation of their own due to jiggly motions, but stars are hot enough such that most of the light is visible light, not infrared. So unlike a basketball, a star doesn't shine mostly by reflecting the light from something else. It shines mostly by emitting light of its own. And a basketball does as well in the infrared part of the spectrum, but in the optical part of the spectrum, it mostly just reflects light. Question there. Can we dampen the lights a bit? Okay, yeah, maybe just in the front here. Not in the back, because then it tends to, get people to sleep. But if you could damp the lights on the screen, that would be great. Anyway, you can see that there are colors there. And so it turns out that the color of a star is first and foremost an indication of its temperature, not of its chemical composition or anything like that, but rather of its temperature. Question? If a star gets hot enough, will it get into the ultraviolet? Yes, it will, and I'll be covering that today. Okay, but yeah, you're already on the right track. I said on Wednesday that cool stars emit a lot in the red. Medium temperature stars sort of look white. They peak, thank you, in the yellow-green part of the spectrum, but our eyes perceive that as white because they're blues and reds as well, and the whole thing is what we call white light, and Newton and others found that white light is a bunch of colors of the rainbow. Then hotter stars still produce blue light predominantly, and even hotter stars produce ultraviolet light. So indeed, and we will see the quantitative relationship in this lecture. Okay, what's your name? Steve. Okay, Steve, very good. Now, ignoring those absorption lines, which are very important because they tell us the composition, but for the moment, ignoring the absorption lines, it turns out that you can describe the light emitted by a star, the spectrum of the light, as though the star were what's called an ideal absorber and an ideal emitter. A black body. Now that's a technical term, a black body. Well, a black body is what? Well, it's something that absorbs all the light that's incident upon it. It doesn't reflect any light. So it doesn't reflect any light, so it appears black. And it doesn't transmit any light. It's not like a transparent pane of red glass where it transmits red light and doesn't transmit other stuff. A star doesn't reflect light and doesn't transmit light. It only absorbs light. However, an object that absorbs light can also re-emit light because there's particles jiggling around inside. And so a star can emit light, and the light that it emits is predominantly light that it produced as a result of nuclear reactions in its interior. It's not that stars shine mostly because they absorbed other stars' light and then they somehow re-emit that. They emit light that they produce within themselves through nuclear reactions. But the point is that a star resembles a black body insofar as it doesn't reflect any light and it doesn't transmit any light. It can absorb light, although that turns out to be sort of just, a minor effect. Mostly, a star produces light of its own because it's got hot electrons and atoms jiggling around inside. And such an object, where you have just light emitted by the jiggling motions of the particle within it, is called a thermal emitter. It's thermal because therm refers to heat energy. It's sort of the heat content, the jiggling motions of the particles inside, and the jiggling particles, being charged, emit light. And something that emits a spectrum of light that's only dependent on the object's temperature and not on its chemical composition or anything else is one of these perfect absorbers and emitters and is technically then a black body. Now, none of these things are perfect black bodies, but they're a reasonable approximation to a black body, and the spectrum looks something like this. It doesn't have much light in the ultraviolet, at least for a star like the sun, and it peaks somewhere, in the blue or green or yellow part of the spectrum. The star is a bit hotter than the sun because it's peaking in the blue or violet, and then it dies off into the red. And this characteristic shape is the shape of the spectrum emitted by one of these perfect absorbers and perfect emitters. And here are a bunch of these shapes, brightness versus wavelength or color. And you can see already then what Steve was hinting at. The cooler objects emit more of their light, a greater proportion of their light, in the red or even the infrared part of the spectrum. The hotter the object, the more it shifts toward producing a preponderance of light at bluer colors. And even hotter stars, emit mostly in the blue or even the violet part. And a really hot star might emit most of its light in the ultraviolet. Okay, so it's that kind of a thing. Now, here I've labeled these guys with the temperature in kelvins. These are the absolute temperature scale. And this is figure it out 2.4 on page 34 of the book. And probably many of you are familiar with this. We in the United States use the Fahrenheit scale. Almost no one else in the world except England, uses that. But we're kind of a backwards country. So anyway, most people use the Celsius scale, where water freezes at 0 degrees and boils at 100. In the Fahrenheit scale, it freezes at 32 and boils at 212. Don't worry about that too much. I don't really care about the conversion between Fahrenheit and Celsius or centigrade. More important is the conversion between Celsius and Kelvin, the absolute scale. On the absolute scale, 0 is the lowest temperature. So that kind of makes some sense. At least in terms of classical physics, all motion stops at 0 degrees. So usually I'm bumbling around up here. If I were at 0 degrees Kelvin, I would be frozen solid, Now, there'd be a little bit of quantum jiggling still, but don't worry about that. On that scale, water freezes at 273 and water boils at 373. So the relationship between Celsius or centigrade and Kelvin is quite obvious. Add 273 to Celsius and you get Kelvin. And that's relevant to one of the homework questions. I'm sorry, by the way, that I didn't cover all of the material for this week's homework by Wednesday. I meant to, but I fell kind of behind because I got interested in quantum mechanics and relativity. And you'll permit me such diversions occasionally, because I think they do interest many of you. Okay, so with that information, you can now do that one problem. So now, let us, and then in a minute I'll show you the other problem. So let us look at this little display, which shows on the right here the temperature of a star, let's say. There it is, 5,775 kelvins. And here's the wavelength of the peak of the spectrum in micrometers or microns. And 0.5 microns is the same thing as 5,000 angstroms. So there it is. It's peaking there at about the yellow-green part of the spectrum. And that's a sun-like star. Our sun has a temperature of 5,800 degrees Kelvin at the visible surface. Now, it peaks in the yellow-green here, but because there's also some violet light and blue light and orange and red, the whole thing together is seen physiologically by our eyes as white, okay? White light is this combination of, violet and blue and green and yellow and orange and red with the precise amounts of the different colors being given by the height of this curve here. And we perceive that combination as white light. So many people say the sun is yellow, and that's simply not true. If it were only to emit yellow light, yeah, then we would see it as clearly very yellow, okay? But it emits all sorts of other wavelengths as well, and physiologically, our eyes and our brains interpret that as white. Now let's see what happens if we decrease the temperature of the star. You see the peak of this curve shifted to redder wavelengths. And if I could go below 4,000 degrees, it would shift way into the infrared here, kind of like the basketball. And if I go to very high temperatures, conversely, darn it, for some reason it's not doing it. There we go, let's go up here. You can see it shifting. Let's go to 8,000 degrees. Look at that. Now it's peaking right at the boundary of the ultraviolet and the violet sort of there. So actually it's peaking at 0.37 nanometers, which is technically right around at the border of violet and ultraviolet. We won't care too much about the exact boundaries and stuff. But you can see this basic idea that the cooler objects emit more of their photons at redder wavelengths than the hotter objects. So now you can understand this hot iron poker, okay? The hot iron rod, and we discussed this, or you're supposed to discuss it in the homework. You start heating a rod in a propane, flame or something like that, and first you don't see it glowing at all. You only see it by reflected light, although if you were to touch it, it would already appear hot. All right, it's just that most of the light that it's emitting is way off into the infrared, and you can't see it. Then it starts glowing sort of a dull red or a dull orange. It's still emitting most of its light in the infrared, but it's now hot enough such that the tail end of the light, let's go back to this one here. Let's go to, like, say, 4,000 degrees, let's say. Okay, so most of the light is infrared, but the tail end is now filtering into the optical region, and it begins glowing sort of red. Then you start heating it up more and more, and then it becomes kind of a bright orange, and then it becomes white because it's hot enough that it has sort of a distribution of light that kind of looks like that of the sun, and that we perceive to be white. And then if you kept on heating it even more, it would turn bluish because it got really hot, okay? So it would be kind of like this star right here, okay? That would appear distinctly bluish because now most of its light is being emitted in the ultraviolet, which you can't see, or the violet, which you can, and the blue, which you can. So there's a shift, okay? And I have to keep going back here. And if you look at this quantitatively then, they're the coals. The coals are emitting most of their light in the infrared, but you can see a little bit that is coming out at orange and red wavelengths. Okay, now quantitatively I want to show you some relationships between these curves because it's really very interesting. First, generically, all of these curves are called Planck curves after Max Planck, and I forgot to load his photograph, but you saw it in the previous lecture where I had him next to Einstein. I asked them to pose together some months ago, and well, if you believe that, I've got this bridge I can sell you. Anyway, these are the curves that are emitted by these thermal or black body emitters. Stars are not perfect curves like this, but they're close enough, and you can understand stars to a pretty good approximation. At least you can understand their continuous radiation if you study them as though they were these perfect emitters. So generically, all these curves are described by a formula that only has temperature. That's the only variable. Chemical composition is irrelevant. Shape is irrelevant. History is irrelevant. The only relevant thing is the temperature. That's the cool thing about a black body, even a hot black body. It's also a cool thing about a cool black body. I just thought of that, and that was a pretty lame joke. Anyway, so here they all are, and here these four curves labeled by 1, 2, 3, and 4. And you might already guess qualitatively from what I've said that curve 4 corresponds to a harder object than curve number 1. And indeed, curve 4 corresponds to a 7,000 degree black body, and curve 1 corresponds to a 4,000 degree black body. Now, it turns out if you multiply the temperature by the wavelength in each of these four cases, you get about the same number. 29 million angstrom kelvins, okay? They're all about the same. Now, they're not exactly the same because I rounded all these numbers a little bit, but if you were to do this on your calculator, you would find that to within a few percent, they're all the same, and if you were to do it right, if I had given you the exact numbers, you would find that the product of the temperature of a black body and the wavelength at which its spectrum peaks is always the same number. It's a constant. So lambda, the wavelength of the peak, that wavelength or that wavelength or that wavelength or that wavelength, times the temperature is a constant. And that is known as Wien's law. It is a subset of the more general Planck mathematical equation. I mean, this doesn't tell you everything about these four curves. It only tells you the relationship between the wavelength at which the curve peaks and the temperature. So this is sort of a subset of the Planck formula. I mean, it's a consequence of the Planck formula. It doesn't tell you the other interesting thing about these curves, and that is that the hotter ones are higher up than the colder ones. I'll tell you about that in a minute. That's the Stefan-Boltzmann law. So Wien's law is sort of a subset or a conclusion from the Planck thing. And so if I give you the temperature of a black body and I give you the constant, and I will never make you memorize that constant. Who cares? It's just some constant. You can look it up in a book, okay? That's not fundamental. But knowing that the hotter objects emit more of their light at shorter wavelengths and cooler ones at longer wavelengths, that's important. And knowing that it's a strictly inverse relationship. That is, if you double the temperature of an object, at what wavelength will the spectrum peak relative to your first object? Double the temperature. Half the wavelength, exactly, all right? What if it's 10 times the temperature? 1/10 of the wavelength. Yeah, exactly right. It's an inverse relationship. All right, now let's go back to the human body and relate this to things that, sort of everyday existence. We in this room are at a temperature of about 300 degrees Kelvin. Okay, now body temperature is something like, 37 Celsius or something, 98.6 Fahrenheit. I don't remember what it is. But it's roughly 30 or 40. And you add 273 to that, and that's roughly 300. And room temperature is roughly 300. So we are roughly at 300 degrees, okay? So if you put 300 degrees into that equation, you would find that we emit radiation that peaks at about 10 microns, or 100,000 angstroms. So we are emitting, our bodies are emitting due to the jiggly motions inside, but we don't see each other that way because that radiation is in the infrared, and our eyes are not sensitive to the infrared. But we are emitting light. We're not a perfect black body, but we're kind of close. We do reflect light, so we're not a perfect black body. Well, stars have absorption lines, so they're not perfect black bodies either. So there, So anyway, but we're not at 0 degrees. We have some jiggling motion, and in the infrared, if you put on infrared goggles or something, well, you need something more sophisticated than that, but you would see each of us glowing with a spectrum like this. But we also emit this kind of a spectrum. But this is the reflected light, either the sunlight or the light from these bulbs or whatever, okay? So we see each other due to the reflected light. That's not the light that's emitted by our own internal thermal motions, jiggly motions, okay? All right, so if you take an infrared photograph of a person holding a match, you see something like this. First of all, he's wearing glasses, and you can tell because the glasses are blue. Again, that's supposed to mean cold. But you'll recall Wednesday's extensive lecture where icebergs and all that are cold and they're blue. But they're blue not because they're emitting a lot of jiggly motion light. They're blue because that's what they happen to reflect really well. And coals are hot and they do emit orange because of jiggly motions. So that part is okay. But anyway, our culture associates blue with cold, and that's just the way it is. So the glasses are not quite at 98.6 degrees Fahrenheit. The guy might be in a cold room, maybe at 70 degrees Fahrenheit. And maybe he just put on the glasses. So the glasses have not yet warmed up to to body temperature. The glasses are at room temperature, so they emit less infrared light than his warm body. And the match emits even more than the warm body. And so the match appears kind of saturated here in this photograph because it emits all this, a lot more light because it's hotter. We'll get to that in a minute. But the point is, here is a picture of a person wearing a tie. He just put on the tie, and the tie is not at body temperature. It's cooler, so it emits less radiation, and it happens to be at longer wavelengths. But anyway, that's what you would see if you were a creature who had infrared vision, all right? And that's this part. But we are creatures with visible light vision, and we don't see that part unless that thing is hot, like a star. Then that whole thing shifts over to the visible part of the spectrum. Okay, is that clear? So here I have all these little balls, and I'll use them more for a demo on Monday, it seems like now, because I won't get to it. But this one, this blue ball doesn't appear blue because it's a lot hotter than this red one. They're both at room temperature. Rather, this blue one looks blue because it reflects blue light better than that one does, and this one reflects red light. The pigments within these balls are different. And that's very complicated. What do different pigments do? Why do they look the way they do? I don't want to get into that. But if you had infrared sensors, you would see that these balls are also emitting infrared light, and they do so with about the same spectrum because both of these balls are at about room temperature. Okay? So don't confuse what you see with reflected light. Don't confuse that with what the jiggly motions themselves produce. Okay, the other aspect of these Planck curves, which I've already hinted at, is that the hotter bodies have a brighter overall spectrum than the cooler bodies. In fact, they're brighter at every wavelength. Even way out here in the infrared, where none of these bodies emit very much, the hotter object emits more light, but it emits disproportionately more light than the cooler objects as you go toward the bluer wavelengths, okay? So the area under these curves rapidly grows with temperature. That is, the area, that is the total energy emitted underneath curve number 1 is a lot less than that of curve number 4. And you don't need to know this, but calculus was designed or invented largely to figure out problems like this. Given a mathematical curve of this sort, what is the area underneath it? You don't have to do those kinds of problems in Astro 10, but that's the kind of thing calculus is good for. Well, when you look at the mathematical relationship between the areas under these curves, you find a very interesting thing. Per unit surface area, a hot black body, and more generally, I will simply say a hot opaque object, because most opaque objects are, roughly speaking, black bodies. They're not perfect black bodies, but they're good enough. So hot opaque objects, strictly speaking black bodies, emit much more energy than cold ones, and the amount of energy they emit is proportional to the 4th power of the temperature. So the energy emitted per unit area, per square centimeter of this object, okay, whatever it is proportional to, and the proportionality constant is called sigma. It's called the Stefan-Boltzmann constant. You don't have to worry about it. You don't have to memorize it. You don't even have to really know that it exists. The energy emitted per centimeter squared per second is proportional to, with some whatever constant of proportionality. And then here's the important part. It's proportional to the temperature to the 4th power. That's the important part. So if I have two objects, one 6,000 degrees Kelvin, another 3,000 degrees, these would typically be stars, and let's, for the moment, say that they have the same size, so you don't have to worry about different sizes. How much more energy is emitted per second by the hot one than the cold one? Well, you take the ratio, 6,000 divided by 3,000, and you raise it to the 4th power. And it's much easier to simplify first, rather than raising 6,000 to the 4th power and dividing by 3,000 to the 4th power. It's much easier to just say that's 6,000 divided by 3,000, which is 2 to the 4th power. And 2 to the 4th power is 2 times 2, which is 4, times 2, which is 8, times 2, which is 16, okay? So the hotter object emits 16 times as much energy per second as the cooler object does, okay? And if it were 10 times as hot, it would be 10 times 10 times 10 times 10, or 10,000 times as much energy. And that's because the hotter objects jiggle around a lot more, and they produce a lot more photons at these shorter wavelengths, but they even produce more photons out in this long wavelength tail, although not much more, whereas they produce much more here. Okay? Now, it turns out we will see that the sun has sunspots. You will see during the discussion sections, you'll go up and look at the sun. It has these sunspots, and it turns out these sunspots are simply cooler spots on the sun's surface. And being cooler than the surrounding regions, they emit less energy per time, per unit of time, And so they appear darker than their surroundings. But if you were to pluck a sunspot out of the sun and put it, alone in the dark sky, it would glow quite brightly. It's like, the sunspots have about the same temperature as cool stars. But they're lower temperature than the average temperature of the surface of the sun. And so they emit less energy per second. And by comparison with the surrounding regions, they look dark. We'll study this more later, but I just thought I'd give you a little bit of a preview of what sunspots are due to. Okay? So now let's go back to this thing, and let's use a little, let's do a little demo again. Little thing right here. Okay, so here you can see the color of the sun. It's not supposed to be yellow. Actually, well, they kind of made it this way, but, it looks a bit yellow there, but it shouldn't be. Anyway, if you made it cooler, it looks red, and it emits not much light, a quarter of the sun's light. You make it hotter, then it emits an amount of light equal to the sun's light. Make it hotter still, it emits, say, 20 times the amount of the sun's light, and now it's starting to look whiter. Make it hotter still, it emits 114 times the amount of the sun's light, and now it looks blue, as it should. This is pretty good. I didn't make this little applet. They made the sun look yellow, which they shouldn't have. They screwed up. The sun at this point should look white, then a hotter star should look blue, as it does. And even hotter looks even bluer. But the point is, as I raise the temperature here on this bar, can you see that? Yeah, you can. The luminosity relative to the sun, the power, the amount of energy, the oomph emitted per second rises quickly. Look at this. This guy is 36,000 degrees. That's only roughly 6 times the temperature of our sun. But the amount of energy it emits is 1,432 times greater per second, Now here we've kept the radius of the sun the same. Now suppose we go back to the sun, around 5,800 degrees, something like that. There it is. Well, pretty good. They made it look yellow. Well, bad boy. Anyway, they screwed up a little bit. It shouldn't look yellow. It should look white. Yeah, there we go. 5,728. That's nearly the temperature of the sun. There we go. That's about the temperature of the sun. 1 solar luminosity. Looks yellow, should look white. Tisk, tisk. Okay. Now let's vary the radius. If I increase the amount of area that's emitting, that can also increase the total power emitted by a star. Right? Because there's more units of surface area doing the emission. Remember, the Stefan-Boltzmann law told you how much something emits per unit area. So to get the total luminosity or power or oomph, energy per second, you have to multiply by the emitting area. And the emitting area grows with radius. So if I now increase the radius of the star, you can also see the luminosity going up. Now I'm keeping the temperature the same. Darn yellow star. Should be white. Sorry. It's a pet peeve of mine. Not that I'm racist or anything. I don't care what color anyone is. But the sun simply is white. I'm sorry. That's just the way it is. I like black holes and red dwarfs and blue supergiants too, so I'm clearly not racist, okay? So you can see that if I change the radius of the star, the luminosity also goes up, all right? By what factor does it go up? Suppose I double the radius of the star. Any guesses as to by what factor the total power or luminosity will go up? Yeah, squared. So it's square 2. 4. Yeah, it's not that hard. How about if I make the sun 10 times as big in radius, but I don't change its surface temperature? How much would its power or luminosity increase? Factor of 100, that's right, because the surface area, 4 pi r squared, grows as the square of the radius. So very good. All right, so now, here are 2 stars that are bound to each other. They're at the same distance from us. This is the Cal star, Albireo, blue and gold. You can see it during the star parties. Some of you have already seen it. How many of you have already seen the Cal star? All right, cool, huh? Well, one of them's hot, one of them's cool. This one is the hotter one, right? Because it's the bluer one. And your eyes see this much better than this photograph does. That's the cooler one. Now, this one looks larger than that one, but that's just an artifact of the photographic process. Even through a telescope, all the stars are basically points of light. So this one is brighter. It got exposed more, so it looks bigger. But from the photograph, you can't tell that it's bigger. Just because it looks bigger doesn't mean that it's bigger. It just means that it's brighter. However, do you think that it really is bigger than the blue star? And if so, why? Well, the blue star emits more, if anything, per unit area, right? Because it's the hotter star. And the Stefan-Boltzmann law says that it emits more light per unit area. So if the yellow, cooler star is brighter, and they're both at the same distance, so you can't invoke different distances the way you can with headlights of a car of different distances, okay? They're both at the same distance, whatever number of light years. So if the yellow star emits less per unit area, but overall looks brighter, what must be true for the yellow star? It must be bigger, yes. So it turns out it is bigger, but you can't deduce that just by saying, oh, it looks larger on that photograph. You see what I mean? The apparent size on a photograph is irrelevant. It happens to be relevant in this case because they're both at the same distance, and looking bigger makes it look brighter, or being brighter makes it look bigger, I should say. But that's just an artifact of the photographic process. So it turns out that this is a dying star. It's a star that's either a red giant or on its way to becoming a red giant. Red giants don't have to be perfectly red. They can be various shades of yellow or orange. We'll study them later. But it's a dying star. Our sun will turn into a red giant someday. It'll become much more luminous than it is right now. All the oceans will evaporate away. Life on Earth will cease. Indeed, the sun might become as big as Venus's orbit around the sun, or maybe even out to Earth's orbit. Probably not quite out to Earth's orbit, but it'll become pretty big, okay? So anyway, putting all this quantitatively, and we'll study this more later, so I'm just introducing it early just so it can start gurgling, percolating in your mind. But we'll study it more later when we study the power of stars and the sizes of stars and the temperatures of stars. I'm introducing quite a bit of physics early just so it percolates longer in your brain, and that way, when we do it for real, it'll be already familiar. Anyway, the luminosity, or power, or total energy emitted per second by the entire object, is clearly dependent on both the energy emitted per square centimeter per second, that's the Stefan-Boltzmann law, the sigma t to the fourth thing, and it's also clearly proportional to the amount of emitting area. And for a spherical star, that's a particularly simple formula. The surface area of a sphere is just 4 pi r squared. So knowing this, you can actually derive the radius of a star if you happen to know L, if you know its luminosity, and I'll tell you later how we can figure that out, and also if you happen to know T. Well, you already know how to figure out T. How do you figure out T, roughly speaking? From what? We just talked about it. Whose law? Wien's law, right. Wien's law, which is a subset of the Planck law. Stefan-Boltzmann law is also a subset. But Wien's law tells you lambda max T is a constant. So go and measure the spectrum, measure the wavelength at which the spectrum peaks. From that, you get the surface temperature. So that gives you this. How do you get the luminosity? Well, I'll tell you that later. That's a bit more tricky. But if you knew both of those, you could derive the radius. So that's indeed how we know the radii of some stars. I'll tell you more about that later. Okay, we'll see this again later on. This is about as hairy as the math gets in the whole course, and there's not much of it in the whole course. And again, if you get the qualitative picture, that's most important to me. I'm not going to bother you when you're 80, remembering the math and all that and knowing how to work through the math. It's great if you do know how to work through the math, but this course is not focused mostly on the math. It's focused more on the concepts. All right, so the Cow Star. Go see it sometime this semester. Any questions? Okay, so now let's go back and say, all right, we've studied the continuous radiation, but there are also these absorption lines, and they are actually much more interesting because they tell you more about what the thing is made of and stuff. Question in the back, or are you just stretching? Okay, just stretching. All right, the fellow in the green shirt, which means that you're not hot. Well, you might be hot, but you're reflecting green light really well. Okay, so you've got all these absorption lines. And I'll give you the punchline, because I'm not going to get to it all today, but I want you to, sort of think about this weekend as Cal slaughters Minnesota, maybe. And, well, we'll see, so, and, you can say, well, how do we know that the stuff out there is the same stuff that we can measure in laboratories here? Well, the way we know is from these absorption lines, from patterns. Each element, here's the punchline, each element and each ionized species of an element. An ionized element is one that is simply, an atom that has lost one or more electrons. Hydrogen can only lose one. It's only got one to give. Helium could lose two. Lithium could lose three or two or one, whatever. Anyway, each of these things, each element and each ionized species of an element turns out to produce a unique fingerprint, a fingerprint that can be recognized among hundreds, thousands, or even tens of thousands of absorption lines in the spectrum of a star. Here I'm only showing you a few of the main ones, but there are actually tens or even hundreds of thousands of absorption lines if you look closely enough. And by analyzing the spectrum in detail, you can see the fingerprints of the various elements. Even though they're overlapping, it's like you've got thousands of fingerprints all on top of each other, but a trained spectroscopist, sounds highfalutin, but a spectroscopist is simply someone who's trained to analyze spectra. They can see all these overlapping fingerprints and say, yes, there's, quadruply ionized iron in that star, or maybe triply ionized vanadium, or maybe 13 times ionized berkelium, or something like that. Look at that. There we go, berkelium. There's no Stanfordium, notice. Haha. There is californium and berkelium and all these other ones, but yes, indeed. So I have this T-shirt here, atomic weight 247.0703. You have to memorize that for the exams. Not really. I hope that after 5 lectures you're starting to come to know me. Anyway, so how do these spectral lines, which are the fingerprints of atoms, how are they produced? Let's briefly go back to atomic structure, which I've already mentioned once or twice, and you probably learned it in high school. But an atom consists of a nucleus, which has protons and neutrons. The protons are positively charged, the neutrons are neutral. And then a cloud of negatively charged electrons. And in a neutral atom, there's just as many electrons as there are protons. Okay, so there's charge balance. And most of the mass, by the way, is in the nucleus. The electrons are about 1/2000th of the mass of a proton. And the whole thing is perhaps about an angstrom in size, roughly an angstrom. And most of it is empty, it turns out. Okay, the important point is the following. These electrons can't just assume any old energy that they want or desire or that you try to give them. They come only in certain discrete energy levels. And those energy levels and the differences among them differ for the different types of elements and their ionized species. Let's consider hydrogen for simplicity. Everything that I say applies to the other more complex elements, but there you've got all sorts of electrons to deal with, and it becomes much more complicated, okay? So let's just deal with hydrogen. Just one proton, just one electron. Turns out the energy levels are particularly simple, but they illustrate what's going on in all the atoms, okay? So here are these discrete energy levels that electrons have, and here's hydrogen in the ground state. People used to talk about orbits, and we told the joke about the Bohr orbits last time, how something became boring. What was the joke? I forgot what the joke was. But anyway, you learned these perhaps in high school as Bohr orbits. Well, they're not really orbits. The electrons are sitting around in some quantum mechanical probabilistic distribution, and you don't even really know. Indeed, the atom and the electron don't even really know where the electron is until something or someone decides to measure it. It's amazing. It's sort of everywhere at the same time with certain probabilities of being in certain locations. And until you actually go and measure it, it's not at any particular location. We'll talk about that more in the bull sessions. Nevertheless, people call them orbits, like planetary orbits, but I just wanted you to know that's wrong. It's just wrong. But there are pretty discrete energy levels, okay? So you've got the lowest energy level is down here, okay? And then the higher energy levels are out here. And indeed, in general, the higher energy levels are spaced farther away from the nucleus. So I put orbits in quotes here. But the important thing is that the outer energy levels are of higher energy than the inner ones. Now, you can't just give any old energy, just a second, to this electron. You can't give it an amount of energy that puts it in between two levels. You can only give it amounts of energy that bring it up to the next level, or 2 levels higher, or 3 levels higher. And by the way, I only drew 4 levels here, but for an isolated hydrogen atom, technically there's an infinite number of levels. Anyway, for hydrogen atoms in a room, they collide with one another, and it turns out the outermost energy levels cease to exist. But if there were only one hydrogen atom in the universe, it would have an infinite number of energy levels, ever more closely spaced out here. So I've only drawn 4 of them. So you can't give the electron an amount of energy that puts it in between. So this is like a parking meter. And some of you laugh, but I like going around taking pictures of people and things, and I might even take a picture of you one of these days. You can give a nickel or a dime or a quarter to a parking meter. See, it says that. But you can't give it 17 cents, okay? It's not allowed. It's forbidden by the laws of meter mechanics, okay? Can't give it an arbitrary amount of money. Just like the laws of quantum mechanics don't allow you to give the electron any arbitrary amount of energy. You can only give it certain amounts of energy that bring it up to other allowed energy levels. So for example, a photon, E equals h nu, denoted by this squiggly line here, might have just the right amount of energy to be absorbed by this electron and to be kicked up to the 3rd energy level. Turns out that requires an ultraviolet photon. If I were to draw it ultraviolet, you wouldn't see it. So I did the next best thing. I drew a violet one. All right, but it turns out you need an ultraviolet one to go from the so-called n equals 1 to the n equals 3 energy level. And you need a precise energy. If you had maybe 10% more or 10% less, that would be way off. Even 1% more and 1% less would be way off. These are very well-defined energy levels, it turns out. Okay? Now, suppose you started in the 2nd energy level. Turns out that to get to the 3rd or 4th or 5th, you can do that by absorbing a certain kind of optical photon. In particular, in going from the 2nd energy level to the 4th energy level, a hydrogen atom, or the electron in the hydrogen atom, can absorb a green photon. Not just any old green photon. It has to be a particular wavelength of green. But for our purposes right now, in comparison with red and blue and violet, let's just call it a green photon and not worry about precisely what wavelength it has. So you've got all these photons going through this atom. The atom is transparent. It's transparent to most of these guys, the red, blue, and violet ones, because they don't have the right energy to raise an electron from the 2nd energy level to any one of the other allowed levels. These guys have the wrong energy. But this particular green one happens to have the right energy to be absorbed by that electron and to kick that electron up to the 4th energy level. So that photon is no more. It has ceased to exist because its energy has been gobbled up by this electron, and now the atom is in an excited electronic energy state. Okay? And the energy of the photon that was absorbed is equal to the difference in energy. Uppercase delta means a change or a difference in physics speak. The change in energy, or the difference in energy between the 4th energy level, E sub 4, and the 2nd energy level, E sub 2. There's some difference in energy between those two. Delta E, that is the energy of the photon absorbed. And that photon had to have a frequency nu, looks like a V here, that should be a nu, a Greek nu, having the right value. It couldn't just be any old frequency. It has to be that frequency which, when multiplied by Planck's constant, gives you this energy difference, delta E. Okay? And, you can also put in hc over lambda here as well, because the frequency times the wavelength is the speed of light. Now, once the electron is up there, I'll tell you one more thing, and then I'll start Monday's lecture with some cool demos where you can throw balls at me and kick me and all sorts of things. So come on Monday, you have a chance to kick your professor. Anyway, once the electron, and throw balls at your professor. Anyway, once the electron is up at that upper energy level, I'm also going to electrocute a pickle on Monday. Okay, some of you, those in Anand's discussion sections have already seen this, but anyway, we're going to electrocute a pickle and hopefully not electrocute ourselves. But once the electron is in the upper energy level, it's lazy. It doesn't like being up there. And in a tiny fraction of a second, typically, it will come back down. It can re-emit a photon. And it doesn't have to go down to the second energy level. It could go down to the third one first, and then the second one, then the first one. Or it can go directly to the first one. Or it can go to the third one and then the first one. It can do any allowed combination. It can cascade down, whatever. But the point is, it can re-emit a photon, and that emission occurs in a random direction. It is not necessarily the direction in which the green photon was originally going. So even if this electron decided to jump back down to the second energy level, in general, it will not produce a green photon going the same way that it originally was. In general, it will go in a different direction. So you've lost a photon as the light went through that gas, and that, my friends, is what will produce a green absorption line in the spectrum. You've lost some green photons as the light was going through that gas, exciting electrons up to the fourth energy level. So there's a deficit of light at green wavelengths, having that precise wavelength, and that is what produces an absorption line in the spectrum. Okay, more on Monday. Go Bears. By the way, usually you get a bunch of absorption lines, but I'll talk about that on Monday. Okay, have a good weekend.